Hello, everyone, and welcome to Chapter 2, the nature of molecules and the properties of water. So, in this chapter, we're going to discuss a lot about really, the simplest kind of building block that we actually creates life, which are literally, molecules, and what these molecules are even actually made from. So, even going to even smaller building blocks, which are elements and atoms. So, really, for us to understand actually life, we need to understand these literally building blocks that I'm talking about and how these all of these come together to create literally molecules that then create macromolecules and etc. and then which is life and how these come together. These kind of, as we all know, when a lot of these different molecules come together to create compounds or bigger structures, these emergent properties come out. Now we're going to talk about, one big emergent property of water and how different literally molecules came together to create water and how the emergent properties has actually allowed us to live and why it's so important for us to actually live. Not just because we're thirsty and we need water, no, we need water for so many different types of functions and it's purely because of its properties. Always think about like why don't we need, for example, some other liquid to survive? Why is it water? Why is it H2O? You know, and it's mostly because of its emergent properties that came out that are super important for us. So let's start into let's give it like a nice introduction to this. So, as we all know, 12.5 billion years ago, a huge explosion happened, which is basically what we call the Big Bang Theory. And this is what started the universe. So this is a theory. There's a lot of evidence or a lot of basically kind of experimentation to support this that actually show that the Big Bang Theory happened 12.5 billion years ago. Then fast forward to 4.5 billion years ago, Earth was formed. 1 billion years later, life started. And these are most probably the most common ancestor that came out and then later on started to diversify bit by bit. Fast forward to now, for us to really start to understand, be it our most common ancestors or basically the plants or the animals or anything from that in a more, let's say, research manner, pharmacological manner, or medical manner, if you want to understand this kind of forms of life, it's extremely important for us to learn the building blocks of all of life. We need that, because we cannot, because again, it's because of these building blocks that come together that emergent properties come out. And we need to know what those building blocks are. So, really, we're going to go into one of the most smallest kind of building blocks, which are atoms. So, let's define, first of all, matter. Matter is any substance in this universe that has mass and occupies space. So, anything that literally has mass and occupies space is matter. And basically, matter is composed of atoms. So technically, how matter gets mass and space is because of atoms. So it could be as us, we as human beings, we're covered in atoms that gives us mass and space. But it could also be literally basically this piece of wood. This wood has a mass and it occupies space. But that wood is composed of atoms that come together to give that mass and space that then give us matter. So for us to understand biological molecules in the wild or basically inside of us, we need to know the structure of atoms because these atoms are exactly what create biological molecules. So it's key to understand the atoms. So saying that, let's get to know what atoms are. Let's dive into that. So let's look at the structure. Atoms are literally what make elements like oxygen, nitrogen, or basically fluoride or whatever. Fluoride is literally made up of the exact same type of atoms. Atoms are made of subatomic particles, which are protons, neutrons, and electrons. Protons and neutrons are literally found both in the nucleus of an atom but they differ in their charge. Protons are positive, neutrons are neutrals. They do not have a charge. Electrons are not found in the nucleus, they're found outside. But similar to protons, they do have a charge, but it's the opposite. Electrons are negative. So they differ in protons in that they do have a charge like each other, but protons are positive, electrons are negative, and electrons are found outside the nucleus. They're basically around the nucleus and they're found in orbitals, which I'll be explaining much more about a bit later. But this is literally how an atom looks like. So if we take literally the element hydrogen, this is what it's made of. It's literally made of atoms that are basically made of one proton and one electron. If you look at the element oxygen, it's made of atoms that are made of eight protons, eight neutrons, and electrons. And here you have basically this nice little key. So these kind of white balls are protons, these small little green balls are electrons, and these literally kind of, balls that are made of blue are neutrons. So you see that, for example, here in oxygen, that protons and neutrons are inside the nucleus, and outside you get to see the electrons. So this is basically where they're found. But do you see one thing that is quite unique here with hydrogen? There's no neutrons. All atoms actually have in their nucleus protons and neutrons. The only exception for this is hydrogen. Hydrogen has only one proton. It has no neutrons. That's the only exception, but every single type of element or atom, sorry, is composed of protons and neutrons and electrons as well, except for hydrogen. Hydrogen does not have neutrons. That's the only exception. But one thing that we basically can differ between atoms is something that is called the atomic number. So atomic number is exactly how many protons does an atom have. So hence the atomic is literally inside. How much is basically the number of protons inside? Every atom of a particular element has the same number of protons. So for example, oxygen, if you look at here, as we said, oxygen is made up of the same atoms. And basically, if you look at the atoms, they all have eight protons. So that's what gives oxygen. So oxygen has it basically has eight protons, hence the atomic number is eight. Hydrogen has one, hence basically the atomic number is one. So if someone tells you what is the atomic number, you tell them basically the number of protons. And this is extremely important because the number of protons or the atomic number, it tells you actually a lot about the chemical properties. Is it, for example, basic? Is it acidic? Is it basically has a charge or not? Or what's it called? It tells you a bit about its chemical properties. That's why the atomic number is extremely important. So the number of protons usually is equal to the number of electrons if it's neutral. Atoms are generally electrically neutral because they have the exact same number of electrons and protons. So look at oxygen here, 8 protons, 8 electrons. So basically if you add them up, it's 0 because this is plus 8 and this is negative 8 because this has a negative charge. Neutrons has no charges, so you don't really care about this. And as we know, an element, so as we all know, element is literally made up of the exact type of atoms. So literally atoms are the building blocks of an element, like oxygen. Oxygen is all made up of basically literally atoms that have eight protons, neutrons, and electrons. I'm repeating this, I'm really sorry, but just to keep this in mind, what's the difference between elements and literally atoms? Think about literally atoms as the building blocks of elements. But an element, what is an element? Is literally a substance that cannot be broken down by any other substance by ordinary chemical means. So basically what that means is a substance that cannot be broken down by chemical means. But I can break this. I can break, for example, oxygen is an element. I cannot break oxygen by chemical means, but I can break it by physical means. I can actually get oxygen and let them spin at the speed of light, and if they crash together, they literally will be able to be broken. So it's extremely important, these definitions. By any substance that cannot be broken down to any other substance by ordinary chemical means. You cannot break it down to other substances by chemicals. So please do not get confused there because I can bring up in the exam, oh, I can break it basically this down by physical means. Does that mean is it an element? Technically, yes, it can still be an element as long as you cannot break it down with chemical means. Then you have something called atomic mass, when it comes to an atom, the atomic mass is literally the mass, how much literally substance is there. And that's usually the amount of protons and neutrons. So sometimes we, of course, we want to see how much does it literally, how much substances is there. But something that's quite interesting is that protons and neutrons are there. There's no really mention of electrons. Can anyone, can I guess why if you start thinking about this? It's purely because protons and neutrons, they all weigh approximately 1 Dalton. Electrons weigh 1 over 1,840 times less than 1 Dalton. So technically, their size or their mass, sorry, is almost negligible. So that's why. So you can add electrons, but it's not really going to change it. If you add the number of protons and neutrons, you get your atomic mass. That's why we kind of ignore electrons because they're negligible. They're literally mass is not it's not really that much. It's literally negligible. But to give you in some sort of way how much 1 Dalton is, to kind of put this as a reference for you, literally 1 gram is equal to 6.02 times 10 to the power of 23 Daltons. That's how much 1 gram is. So Dalton is extremely very small because, as we know, one gram for us is nothing. We are in the kilogram scale when it comes to human beings. So imagine 1 Dalton. But please do not confuse, please, I beg you, do not confuse mass with weight. Mass refers to the amount of substances, so how much substance do you have? Hence, when it comes to atomic mass, we're looking at how much the amount, so the sum of protons and neutrons. Weight refers to the force gravity exerts on substances. That's different because my mass, no matter where I am, basically if I'm in Mars or if I'm on Earth, it's the same because it's the amount of substance I have. The weight changes. My weight here on Earth is completely different to my weight on Mars because the gravity is different there. So let's talk a bit more about a subatomic particle of the atom, which is the electron, which is extremely important. As we said, it literally doesn't weigh almost anything. It's negligible. That's why we do not take it into account when it comes to the atomic mass. But electrons are still extremely important. They do not weigh much, but still, let's say, have a heavy contribution to the atom. So electrons are negatively charged particles that are located in orbitals. And I'll be talking about what orbitals are in a second. But technically, as I was saying, in generally neutral atoms have the same number of protons and electrons. And what happens is that in the nucleus, the protons are literally keeping these electrons together because, as we know, positive and negative attract. So inside the nucleus, you're attracting or you're keeping these electrons to be orbiting around the nucleus, to be going around that nucleus. But sometimes what happens is that there's going to be external forces that's going to literally kind of steal that electron away. Or, or the electron or basically electrons will be actually coming into the atom. Suddenly, basically, the atom is able to, let's say, grab another electron, not basically lose it, but gain another one. So what happens now is that you have an unequal number of protons and electrons, and then you have an unbalance. And this is what we called ions. Is suddenly when these atoms lose an electron or gain one. And then they have either a positive or a negative because suddenly if you gain one extra electron, you have an extra one positive, sorry, if you gain one electron, you have one negative charge. If you lose one, you gain a positive charge, one positive. And that's what we call cations and anions. Cations is basically literally means that we have more protons than electrons. So in this case, this happens when an atom loses an electron. So suddenly you have more protons. So you have a net positive charge. Anions is literally the opposite. Is when you have fewer protons than electrons, and this usually occurs when an atom literally steals an electron to its orbit, and that usually gives you a net negative charge. So when it comes to basically neutrons, let's talk about them a bit. We have something called isotopes. So as we said, atoms usually have equal numbers of protons, neutrons, and electrons. But in the cases of isotopes, they're atoms of a single element that possesses different numbers of neutrons. So they have different number of neutrons. And this actually can give different certain properties to literally uh, the the element. And what happens sometimes is that when you suddenly have too many neutrons, this can cause actually the nucleus to break because there's too many things already there, and the nucleus becomes fragile. But the issue is that when a nucleus breaks, it's going to start to emit radiation. And this type of radiation is called gamma radiation. I'm not expecting you to memorize what type of radiation, but this is just purely for your interest. So, where mostly isotopes, because they have a lot of neutrons or extra neutrons that the whole nucleus cannot literally bear, it's gonna break and it's gonna decay. So decaying is literally the act of literally disintegrating, and it breaks, and it basically it's the rate at which it's literally breaking down. It literally remains constant, that rate. So we have something called half-life. So it literally means time it takes for one half of the atoms in the sample to decay. So let's imagine, okay, that we have carbon 14, that is an isotope, and it's literally breaking down. And we know that it has a half-life of literally, let's say, 10 days. Okay? So we know that we have, let's imagine, I don't know, 10 grams of carbon 14. So I know that in 10 days, that's going to become 5 because I know the half-life. So how much half of that atom is going to be basically go down to its half. So it's in this case, half-life literally means how much time it takes for one half of the atoms to decay. So that's what we say with radioactivity. We tend to say the half-life. It's like how much does it take for it to decay in half. But I'll give you examples of isotopes like carbon. So you see basically here, this is the carbon. So you have carbon, which basically has 6 protons, neutrons, and electrons. This is usually what is found in nature, like 99%. It has an atomic mass of 12 because there's 6 protons and 6 neutrons. We don't calculate electrons. But in the isotopes, in this carbon 13, we basically call literally this as now it has atomic mass of 13, 6 protons and neutrons. So we literally denote this carbon 13. 13 is literally the atomic mass. So carbon 14, the atomic mass, it literally means that there is literally the sum of protons and neutrons is 14. And in this case, there's 6 protons and 8 neutrons, and if you add them up, you get 14. So these are different kind of isotopes. And of course, the atomic mass, as I said, the atomic mass changes literally the properties of a chemical or basically of an element. So carbon 12 here, as you can see here, is extremely stable. But if you look at carbon 14, no, it's so big, it's much bigger. There's now suddenly 2 extra neutrons, and it's really causing the nucleus to break down and to literally kind of give out this radioactivity. So this is how you see how different atomic numbers can actually give you different chemical properties. But now let's talk about the electron arrangement. So as we said, so if you go back over here, we know that inside the nucleus, you have the protons and neutrons. But hanging around the nucleus, just around it, you have the electrons. And honestly, the electrons per se, to really put them in one exact place is it's impossible. That never happens because electrons are constantly moving. They literally keep moving in something that we call orbitals. And what we define an orbital to be is literally where the electron is most likely to be found. It's literally, if you want to put it also in a more mathematical manner, it's a probability, it's probability distribution where the where the electron is going to be found. So you're distributing the probability of where that electron is going to be in space. That's what literally basically an orbital is. So we know that the electrons are literally in this kind of orbitals. They're basically in this kind of defined space, or literally, or probably in this defined space. And electrons, they are extremely important and to tell you how literally an element is going to, or how how an atom is going to behave. Is it gonna be how it's gonna behave with basically, specifically with other atoms? So how a carbon is gonna react with another oxygen? It all depends on its electrons, and I'll be explaining a bit why per se that's the truth. But I want to give you an example of these orbitals. So in general, we have these two different types of orbitals. We have basically the s orbital that literally looks like a sphere. So this sphere is literally the probability of where that electron is going to be. So around this space. Then we have something called the p basically orbital, and they look literally like dumbbell looking structures. So this is exactly, so this is how, or the electron is going to be basically placed. So most probably this is how it's moving. So this is probably where it's going to be. To really pinpoint it to exactly that it's going to be here, it's impossible because it's moving constantly. And every orbital has two electrons. So this S has two electrons moving in this kind of manner. This basically p orbital, they are moving in this kind of manner. This p orbital is again dumbbell shaped, but has basically to the y axis, while this one is the z and this is the x. So this is what we mean by orbitals. And why do literally electrons kind of dictate how an atom reacts, or basically how it behaves? To really explain this, I want to show, basically kind of describe to you how far an electron is. Okay? So let's imagine you have a golf ball in your hand. Okay? That's your nucleus. That golf ball in your hand is your nucleus. The closest electron to that golf ball or that nucleus that's in your hand is 1 mile away. So literally atoms are mostly consisting of actually empty space. If between the nucleus and that electron is 1 mile away, it's crazy how far these distances are. And this is why, uh, because in generally when one atom basically goes and interacts with another atom, the nucleuses are never going to touch. So that's why the electrons that are far away are the ones that dictate how they behave, because these ones are not going to be touching the nucleuses. It's the electrons of the different atoms that are going to be playing with each other. So that's why the behavior is locked to them. So really, to memorize that concept, it's extremely important to know why, and that per se. So, as we said, electrons are found in these orbitals, which is literally the orbital is literally a distribution or of probability of where that electron is going to be. And it's literally there, we have s orbitals that are literally spheres, or they literally are p orbitals that literally look like dumbbells. So those are literally where the electrons are found, okay? So now one thing that I also want to talk about is energy levels. So to really actually explain what energy levels are, I want to speak about, I want to give you an analogy, okay? Let's imagine I have a grapefruit in my hand. Literally, that grapefruit has potential energy. That potential energy meaning that if I basically literally, drop it from my hand, suddenly this grapefruit is gonna fall down, or suddenly it's gonna have energy to go down. That's what potential energy is the energy that you're going to have. It's not kinetic, it's kinetic is in motion. Potential is resting, but you still have energy because literally that grapefruit in my hand, if I remove my hand, it's gonna drop down. Okay, so let's imagine this is basically I have this grapefruit, it has a certain potential energy. So let's imagine now I go somewhere higher. So let's imagine I go to the roof and I literally put my hand and extend it to the outside. Suddenly now this grapefruit has much more potential energy because now if I drop it, I'm gonna drop it from much more far and it's gonna literally get much more kinetic energy. This is what energy levels are. Literally, energy levels are how much energy does that electron half. So if we look at the nucleus over here, think about this as literally the steps. If electrons are in this step, which we call the K, they have a certain energy. If these are the L, they have more energy. If they have the M, they have more energy. If they have the N, more energy. Just think about it. If this nucleus over here right now wants to attract this basic electron out there, it needs much more energy because it's so far that it needs to exert so much energy to keep it in its distance, basically around it. If this electron goes down to the K, it has less potential energy because the nucleus is exerting less energy there to keep it there. So that's what you have to remember. Energy levels is literally what we call them quanta, specific amount of energy. So it literally tells you where, like how close to the nucleus is and how much energy it is, because the distance tells you how much energy. If it's very close to the nucleus, it means it has less energy compared to when it's outside of the nucleus, like bit more further of the nucleus, sorry. So things not to confuse, energy levels and orbitals. Orbitals are literally three-dimensional shapes that indicate where the electron is most likely to be located. So literally it's a distribution, it's a probability distribution of a 3D structure of where that electron is going to be. Energy levels are drawn as rings to indicate an electron's energy, how much potential energy that electron has, and that depends on how far away it is from the nucleus. So within an energy level, you have orbitals. So basically, I'm going to be explaining, for example, here the K orbital. The K orbital, the K, oh, sorry, I'm very sorry. Not orbital, the K energy level has only one orbital, which is 1s. So basically can allow two electrons, because as we said, one orbital can allow two electrons in there. So this energy level K can only accept two electrons because it only has one orbital. Then we have a further one up, which is the L. The L can accept now one s orbital and three dumb shell shaped, basically, orbitals. So hence it can contain up to 8 electrons because 2 from the spherical and 6 from the 3p orbitals. That's the energy level. And basically M goes up and N goes up. So you're literally going up. So again, please, let's go this again. So orbitals are literally these 3D structures, which is literally a probability distribution. So probably where the electron is. So S is spherical, while P is much more of this dumbbell. That's what orbitals are. Energy levels are again how much energy, the quanta, the amount of energy that electron has. And it tells you a bit the distance. If it's the K, it's more closer to the nucleus than compared to basically the energy level L. Energy levels are indicating the electron's energy. Orbitals, 3D dimensional shapes, and the electron's most likely location. So this is literally what it is. So imagine that an electron that when basically it jumps from the K to an L, it gains energy. It has much more energy. But if an electron that goes down, it's going to lose energy. And this energy is going to be released outside because now it's losing energy. Its potential energy goes down. It's literally, imagine here the grapefruit in the roof, and then you go down to the class, and then basically, yeah, that grapefruit has less potential energy. This is a really nice video that I will not going to show, but please look at this on your free time. But one thing, of course, is that between atoms and different elements, sometimes what happens is that they're gonna start fighting for electrons. And what's gonna happen that sometimes some will actually lose electrons and some will gain electrons. And in a, let's say, a reaction where one atom gains an electron and the other one loses one, that's called redox reactions. These are literally when electrons can be transferred from one atom to the other. Okay? So the atom that is actually losing an electron, we call it oxidation. But the one that's actually gaining of electron, we call it reduction. And reduction, we call it reduction because it's reducing its charge. So it's going literally, it's getting you're getting a -1, so it's literally reducing. That's why we call reducing. And redox is literally you literally take this RED and this UOX. So it's just to tell you that this reaction there's a reduction and an oxidation happening. So that's the best way to memorize redox. But we're going to be talking a lot about redox reactions in chapter 7. So don't worry about it. You're definitely going to be learning a lot about what these redox reactions are. But let's talk about elements. So basically, there was this really brilliant scientist, as the name here, but it's this Mendeleev. And what Mendeleev is a Russian scientist. He actually went and put literally, elements according to the valence electron. So basically, he made a whole periodic table of all of the elements, and they're arranged based on valence electrons. And what valence electron is the number of electrons in the outermost energy level. Okay, so it's literally. So let's imagine, for example, in the case of, let's say, let's take here an example of carbon. Okay, so carbon has 6 electrons. So if we want to basically kind of put the electrons, we have 2 that go in the K level and 4 that go in the L level. So the valence electrons is 4 because it's the number of electrons that are in the outmost energy level, which is the L. So that's what the valence electrons signifies. Okay. So literally they're literally like this based on the valence electrons. So if you look at here, so hydrogen, lithium, sodium, potassium, and the rest, because I don't know what these stand for, they all have 1 valence electrons. This has 2. Okay, so this is what literally what it means. But one thing that he basically started to realize is that once in the periodic table, there's a beautiful thing that he realized, Mendeleev, is that they start to follow something called an octet rule, meaning that atoms tend to establish completely full outer energy levels. They always want to have a full outer energy level, and usually to have a full outer energy level, you need 8 because the amount of electrons that you can get in one orbital, that is not the K, because K only can take 2, but the others is 8. So L, M, N, they need 8. So atoms are always looking to make sure that they have basically a full outer energy level. Because if they don't, that makes them a bit unreactive. Sorry, that makes them very reactive. They always want to go into an inert kind of state and where they're not reactive. And to do that, they have to have all 8 electrons in their valence shell. Valence shell means the most outer shell. That's what valence is. So valence is, always think about it, what is the most outmost basically thing. Is it the electrons or is it literally the shell? And literally, what he saw, Mendeleev, as was wanted to say, is that literally, if you put them based on their valency, suddenly the columns actually have certain properties. So if you look at basically a column number 1, these are called alkali metals, and they all tend to lose 1 electrons except hydrogen, because hydrogen doesn't really care. It's mostly these guys over here. Hydrogen doesn't want to lose doesn't want to lose an electron. It actually wants to gain an electron. But the rest here, lithium to sodium, potassium, the rest down here, they all tend to lose 1 electron because by losing that 1 electron, their outermost um, valence is literally complete, really. So I'll give you here example lithium. Lithium has 3. So if we go back here, for example, to this kind of stuff here, lithium puts basically 2 here and then 1 here. If it loses 1, suddenly it has energy K level, and that is complete because the K level only has 1 orbital that can accept 2. So it wants to lose it. Well, if let's imagine take now sodium, that's 11. Okay, that's great. Let's go back in here. So K has 2 here, then you have 8, that makes 10, and then you have M has 1. If you lose it, suddenly L is basically that becomes your valence shell, and that has 8 valence electrons. Great, octet rule done. I want to lose it, and same thing goes for potassium. Then If you look at basically column two, it's the same damn thing. They tend to lose two electrons. They want to lose two electrons because that's going to help them actually become inert. Then you have basically these columns 3 to 12, which are morely transition metals. But then basically this column basically 16, these chalcogen are nonmetals. Column 17 are basically halogens. These are extremely reactive because they really want to gain one electron. For example, as you can see here, these really want to because they just need one. So in generally, these halogens tend to really kind of combine a lot with this alkaline earth metals quite a lot. For example, I'll give you an example: sodium and chloride. They love to get together. That gives you salt because this one wants to lose an electron, this one wants to gain it. So these guys are extremely reactive with each other. And then you have the column number 18, which is here, and these ones are extremely inert. And by inert, I literally mean that they're noble gases. They're non-reactive because if you look at all of them, they have a complete valence shell. They have 8 valence electrons or 2 in the case of helium. They don't need anything else. They do not react. They are extremely non-reactive. Like helium, argon, neon, you name it. So by looking, so they actually Mendeleev, when he put it on the valence electrons, he could see that by the columns you could actually have similar properties between the elements. That's just quite cool. And this is all dependent again on valence electrons because he literally put this on basing on valence electrons. And based on the valence electrons, you can actually see how they're going to be behaving. How they can be extremely, let's say, reactive, like for example, halogens or alkaline metals, or are they going to be very non-reactive, like the inert noble gases? So when it comes to the periodic table, as you can see, there's 94 naturally occurring elements. Only 12 elements from those are actually found in living organisms. So if you take a look at this nice, basically here, kind of graphs, or periodic table, sorry, you see here basically the ones that are found in green are the ones that are found in living systems. But then you can see some of them, for example, the silicon has some height. What that height basically literally means is how much or the frequency that's found on the Earth's crust. So what you see something clearly is that not all of the elements that are actually very abundant in the Earth's crust is found within us. Because you can see, for example, silicon that's extremely found in the Earth's crust. We don't have it in our body. It's not really found that much. So trace amounts is literally found in more than 0.01%. That's what trace amounts means. And from these 12 elements that are found in a living organism, 4 elements make 96.3% of the human body weight. And these are basically carbon, hydrogen, oxygen, and nitrogen. Okay? And if you want to basically rank them, oxygen is the most one that is found, then goes carbon, then hydrogen, and then nitrogen. And then basically, why are they basically make 96.3% of our human body? Is because they make literally organic molecules, which is what we're made of. And some other trace elements are extremely important as well for us, like zinc or magnesium. So it's not just because these are the fours that are mostly found in our body are the most important. No, there are some extremely trace elements that are very important, like zinc or magnesium, for example. So when it comes basically to molecules, oh, you know what? I'm going to stop actually here. This is where I'm going to stop. Thank you for tuning in and see you guys in class.